All right, welcome to Unit 9. This is new material. Last week you did have a couple of little assignments to introduce you to a few concepts, but today it's basically new stuff. So you'll need to be looking at your student notes for Unit 9 as we go through these slides. I believe there's 4 parts. It'll come at you this week and next on Unit 9. This unit is called Principles of Natural Selection. Principles of Natural Selection. Most freshmen enjoy this unit and the units after this because so far we've been dealing with things like cells and DNA, which are super small and you can't really get an idea what they look like. Now we're going to start looking at bigger organisms and how organisms have changed over time, how they exist in their environments now. So it's more stuff you can lay your eyes on. You could touch them if they were in the room with you, plants, animals, things like that. So hopefully you're going to enjoy this unit and the ones to come. I know you've all enjoyed the units previously, but hopefully this one will take it up a notch. So natural selection deals with a principle called evolution. Evolution. Now, what comes to mind when you hear the term evolution? Anybody in class with me? Evolution? What, Kendrick? Okay, evolving, which means what? Changing. Very good, Kendrick. What a genius you are. Evolving means changing, right? We all evolve or adapt. Listen, we all evolve or adapt. And teenagers are really good at this. Think about all the different situations you find yourself in. You have to adapt to being a student, a friend, a daughter, a son, sometimes an uncle, an aunt. And think about how you change some of the things that you do. Your personality or following certain rules or living a little more in your freedom. Teenagers are really good at adapting. Now, we'll be talking about adaptations that not necessarily deal with behavior, but more of what's been changed through different organisms, okay? We'll primarily look at the way that they look and how their looks help them survive, okay? So good job on that, Kendrick. Another thing with evolution you may have heard about is people like to think, where did humans come from? Did we evolve from apes, right? Somehow along the way, that's what people believe evolution has come to be known as. The thing is, there's so much more to evolution than that. That's actually the theory of evolution. And theories are things that haven't been proven or they're working on being proven. I like to teach you facts, okay? Theories are what comes after we understand the facts. So I'm going to encourage you, everything that we learn in this unit is factual, real-world information that we have observed. All right, any theories that come from that? Great, wonderful, hunky-dory. But I want us to learn about the facts. So anyway, now I'm rambling for a minute. Let's get on to our notes. All right, so principles of evolution. Evolution, by definition, is the process of biological change by which descendants, what's a descendant? Anybody in my class? Descendant. Offspring, very good, Larson. Give him a shout out. Larson got it. Offspring, you are the descendant of your parents. You are also the descendant of your great-great-great-great-grandparents, okay? You have descended from them. You are offspring in a line of these organisms, all right? Any kids you have one day will be your descendants. It's the process by which descendants come to differ from their ancestors. And ancestors are those who've come before us. Even your parents will be considered your ancestors, all right? This is the rock pocket mouse that we see here. We're going to do a video with him or her in a few days. The rock pocket mouse is one prime example of evolution. What we'll see is they have actually, as a species, changed color over a very short amount of time. Why did they change color? In order to survive. Some of them, say these black ones there, were getting picked off by killers, by hawks, by snakes, and things like that because they stand out like a sore thumb, right? Yes, ma'am.
Would stand out, but the little brown one, hamster-looking one, wouldn't stand out.
It's camouflaged, right? And so think about, good job, Ponce, with the genius move up here. That brown one would be better fitted for survival, right? Which means survival means living longer, having more babies. So think about what those babies are going to look like. Most likely, like the brown one.
Or they could come out black.
They could, but far less chances. Remember our Punnett squares. We could put all that together. See, we could look. Good girl. All right, much of today's understanding of evolution is based on the work of one guy. And that one guy is named Charles Darwin. Charles Darwin, there's his picture. He's a good-looking fellow there. If I ever go bald, I think I'm going to go for that look. But he worked in the 1800s. He lived from about 1807, I think, to 1870 something. So that's when he was working. That's when he was doing his research. We will spend a whole lot more time on him later on. Today, we're going to look at some of the principles right here. Darwin didn't come up with all this on his own. Okay, he built his ideas on ideas that had already been set out by other people. And modern understanding of biological evolution comes from hundreds of years of research. Some people think, oh, it's all based on Darwin's work. No, he was just the driving factor in getting it in the public eye. All right, so let's talk about what he built his knowledge off of. One was in the 1700s, so even before he was born, there was a guy named Carolus Linnaeus. You might also hear him called Carol Linnaeus. Either way, probably not a great thing to be walking around as a dude with your name Carolus. I think you might have some jokes thrown your way. But anyway, Linnaeus was a brilliant person, a brilliant scientist. He came up with a system to organize and name different organisms. Okay? Up until that point, yeah, we had, this is a horse. We call it a horse. But if somebody in a different language is working on some kind of research with horses, they may not call it the same thing. They're definitely not going to. So he came up with a way to give them all a similar name. We'll look at that in a minute. All right, so species. You've probably heard the term species before. Here is the technical terminology for a species. A species is a group of organisms. So organisms are living things. This could be plant, animal, bacteria, amoeba, anything like that. A group of them that first, yes, they can reproduce. So they're going to have babies together. And they have fertile offspring. Now, fertile offspring means that those babies, the offspring, are also able to breed and have offspring themselves. All right, and that is a very fine, clear cut, distinction that has to be made. And here's one reason why. In nature, different species are sometimes able to breed with each other, but their offspring aren't fertile. How many of us has heard of a mule? Anybody work on a farm, live around a farm? You might know what a mule is a cross between? There it is. Good job, fellas. Pennington, shout out. A horse and a donkey. Now, a horse and a donkey can breed together and have a mule. Yes, sir? Oh, we'll talk about that later. That's good. Yeah, I like the way your brain's going. All right, so this mule is really good because it's got the work ethic and the strength of a donkey, but it's in the stature of a horse. It makes it a lot bigger framed animal. If you look it up online, mule, I was looking up some mule stuff this morning, and it said beast of burden. I thought that was a good description because they can carry a lot of burden. They can carry a lot of work on them. Yes?
But ain't they really slow?
They are a little slow, but they're really strong.
We need to keep them inside.
You're right. Get that mule motivated. Stubborn as a mule. You ever heard that? The mules can't have babies on their own. In other words, they're not fertile. Okay, they're not fertile. So that tells us that a horse and a donkey are not the same species, right? Yes, they could reproduce, as it tells us in this definition, but their offspring aren't fertile, as it's called. Okay, so that's the difference. You can also see the same thing if you cross a zebra and a donkey. Anybody know the name of that animal? Donkey. Sure enough, zonkey. A zonkey is what it's called. So I think it's the top left one there. A zonkey. Well, they can't have offspring on their own. They can't have offspring on their own. So, in order for it to be the same species, however, they have to be able to reproduce, and then their offspring must be fertile. Okay, that's the clear definition. Think about dogs, right? We have all these breeds of dogs. They look different. They're way, different characteristics, but most of them are the same species. Can you breed a Chihuahua and a Great Dane? Absolutely you can. Now, I don't want to think of the dynamics of that one. Poor Chihuahua, no matter what we're talking about here. But if I artificially inseminated, let's say one of them, so I did it, took the sperm and egg and we fertilized the egg that way, they can cross and they can have offspring that are fertile. So that tells us even though they're so different, dogs are kind of this special group. They're subspecies of species. But they're still the same species because they can reproduce and their offspring are fertile, even though, man, they look different in some cases.
If different horses can have babies.
All right, so Linnaeus, when he grouped up organisms, he did it according to physical similarities and also if it fit the definition of species. So you might have seen this in a lower science grade, domain, kingdom, phylum, class, order, family, genus, species. Linnaeus came up with that. It's called Linnaean classification, and we will spend, in the next month, we'll take a unit on that. So anyway, we get the names for things from genus and species. You probably heard Homo sapien. That's the scientific, the Linnaean term for humans. Homo is the genus that we're found in. There are other Homo, animals or organisms, excuse me. Sapien is our species name. So Homo sapien. Linnaeus came up with that. So let's talk about the science of Linnaeus' time in the 1700s. Many scientists believed that the organisms on Earth were what was called fixed. In other words, that they couldn't change. Everything looked exactly the same as it always has, right? Every animal that they saw, every plant that they saw had always looked that way. Linnaeus flipped it on its head a little bit, and he said, no, these species can change over time. Yes, Pence?
That's actually happened with elephants. Like they killed the big ones and took their tusks for all the smaller ones.
Had a question in the room, sorry. Linnaeus proposed that species could change over time, okay? Up until that point, everything's fixed. Everything has always existed exactly the way it looks, okay? Linnaeus said, nope, it's got to be different than that. They have changed over time. Why did Linnaeus say that? Great question. It says, why? Why did he say it's different? One reason is about the same time fossils started to be found, okay? And fossils, sometimes we think of them as these impressions in like sandstone. That is one type of fossil. They're imprints, okay? But fossils are traces of organisms that existed in the past. So this could be bones. If looking at humans, that could be things like artifacts, okay? That could be imprints left in volcanic rock, okay? All these are considered fossils. And people started finding these in the 1700s and sharing them. And it started changing the way people saw things because they found fossils that didn't look anything like anything that existed. So think about it. If you say, nope, everything's always existed the exact same way that it does now, then you find a huge dinosaur bone. You go, well, where are the dinosaurs at? They're not here anymore. You have to rethink the way that you've been thinking, okay? Also around that time, dinosaurs were starting to be found. The dinosaurs found in the Mesozoic era, that was the era that they found. Not Jurassic. Jurassic Park led us all to confusion. They started to find these massive bones. And people started going, where are these dinosaurs? And you actually saw a little blowback, people not wanting to rethink the way they thought. And they would say, oh, all the dinosaurs, they're still alive. They just all moved to this island. Or they're underground now. These were real scientific theories that were coming about. You can see that in literature as well. At that time, if you like to read, you've probably read some stories and books and things like that from that time period where they would have mythological creatures that lived in the center of the earth or on islands out in the middle of the Pacific. And that had a lot of tie. Yes, it was fiction work, but it tied a lot to the scientific thought of the day. What were you about to say, Ponce? Now think about the people of this time. I almost want to jump down their throat and be like, you dum-dums, come on, you should have rethought it. But think about their worldview. They didn't have the internet. They didn't have a way to share ideas with lots of other scientists. Even at the time, they didn't have a common place, say like a museum or a college or a university to go and compare ideas. So if you're a scientist and you've got this small place that you live and you observe it for 40, 50 years and nothing has changed in that time, everything still looks the same, yeah, of course, you can only assume that that's the way things work, okay? In today's world, we can see that's far from the way it is, right? And we're going to see with Darwin, probably tomorrow, he was able, to travel to different places and observe some of these changes, okay? We're going to put another video up. I'm running out of 15 minutes, and this is not the end of our notes. So this is part 1A, and look down below here for part 1B.